Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 5 and we're going to look into the subtopic of 5.1 gas. So we're going to answer tutorial question 4, 5, 6, 7 and question 8 respectively. So without any further ado, let us start. So for tutorial question 4, a gas C with a mass of 8 gram at 0 degrees Celsius have a pressure of 0.87 atm and it's occupy a volume which is equal to the volume of 11 gram of carbon dioxide at STP. So we have to calculate the density as well as the molar mass of the gas. So from the question here, we know that the gas C has a mass of 8 gram and occupies a pressure of 0.87 atm at the temperature of 273.15 Kelvin. Because degrees Celsius, we need to convert that into Kelvin. And for its volume, you can say that it occupies the same volume as the 11 gram of carbon dioxide as STP. Okay, so volume dia sama macam carbon dioxide. So we have to find the volume of the carbon dioxide first. So we can find the volume of carbon dioxide by finding the number of mole first by dividing the mass with the molar mass. So for the mole of carbon dioxide, we're going to divide the mass with molar mass, in which the mass of carbon dioxide going to be 11, and then the molar mass here going to be carbon representing 12, and then we have 2 oxygen, which is 2 multiplied by 16. So we're going to have a total of 44. So 11 divided by 44, we're gonna get 0.25 moles. And then from the number of moles of carbon dioxide, we need to find the volume. So the volume can be obtained when we multiply the mole with the molar volume. Okay, so the molar volume here refers to at STP, which is at STP we have a molar volume of 22.4 dm cube. And we can find the volume of carbon dioxide, which is mole of carbon dioxide multiplied by the molar volume at STP, which is 0.25 multiplied by 22.4 liter. And finally, we're going to get 5.6 liter. So you know that the volume of gas C will be 5.6 liter. And then you need to find the density. So the density can be obtained when we divide the mass with the volume. So in order to find the density of C, we need to divide the mass of C, which is 8 gram, and the volume of C here is the same as carbon dioxide, which is 5.6. So 8 divided by 5.6 liter, and once you do the maths here, you're gonna get 1.429 gram per liter. Okay, and for the molar volume, you can use the ideal gas equations that relates the density as well as the molar volume. So you're going to get density is equal to PMR over RT in order to find the molar mass. Okay, so the density here is the same as before, which is 1.429. The molar mass is something that we need to find out. The pressure is given as here, which is in atm. R, we're going to use the 0.08206 liter atm per mole per Kelvin. And then the temperature is also given. So we're going to substitute it into the formula here. Okay, so the atm and atm going to cancel out. The per Kelvin and Kelvin going to cancel out. And then liter with per liter going to cancel out. So we're going to get the unit to be gram per mole. Okay, so once you do the maths here, you're going to get the molar mass to be 36.82 gram per mole. And this is how you find the density and the molar mass for gas C. So for tutorial question 5, when an evacuated glass vessel weighing 134.74 gram was filled with an unknown gas Y, the pressure was found to be 99.3 kilonewton per meter at 31 degrees Celsius, while the mass was 137.28 gram. The glass vessel was then filled completely with water and the mass was 1067.90 gram. by using the ideal gas equation, we need to determine the relative molecular mass of gas Y. So if you read the question like this, it's going to be very hard for you to visualize. So what I will suggest you to do is to draw the diagram so that you can see the situation more clearly. So you can start by drawing the vessel first. So let us read the question again. So when an evacuated glass vessel, so evacuated here means empty glass vessel. The empty glass vessel was weighed 134.74 gram. Next, when it is inserted with gas Y and it was closed with a lid, the total mass, which is gas Y plus the mass of the vessel, we're gonna get it to be 137.28 gram. And this happens at a temperature of 31 degrees Celsius, in which you have to convert it to Kelvin. And then the pressure that it's going to happen is at 99.3 kilonewton per meter, in which you need to convert that into ATM. Alright, so the glass vessel was then filled completely with water, and the mass going to be 1067.90 gram. So the situation here means we're going to open the gas jar or the glass vessel. So we're going to open the lid. So what's really happened here is that the gas going to escape, and then we're going to put water, H2O. Okay, so the water is filled up, and then we're going to have a mass of water, including the mass of the vessel, which is 1067.90 gram. Okay, and by understanding this, we need to figure out the relative molecular mass of gas Y. So we can start with figuring out the mass of gas Y first. So the mass of gas Y can be obtained when we deduct 137.28 minus the empty glass vessel, which is 134.74. So once we do the maths, we're going to get 2.54 gram. So the mass of gas, sorry, here is gas Y, going to be 2.54 gram. And then what we can do is we can find the mass of the water. So the mass of the water can be obtained when we deduct 1067.90 gram minus the empty glass vessel here, which is 134.74. So we're going to get the mass of the water. And we're not going to deduct with 137.28. Okay, so as what you can see, we don't deduct with 137.28 because the gas Y going to escape when we open the lid, and we're going to put the water. So the gas Y going to escape, and then water going to fill in. And that is why we just deduct it with the empty glass vessel. Alright, so we got the mass of the water here. So in order to find the volume of the gas Y, we know that we need to get the volume of the container, in which the volume of the container is the volume that is occupied by the water, okay, which is 933.16 gram. And we know that the density of the water, so here refer to the density. So the density of water is 1 gram per ml. So in order to get the volume here will be obtained when we divide the mass, which is 93.316 gram, divided by the density of water, which is 1 gram per ml. Okay, so when we cancel it out, we're going to get the volume to be 93.16 ml. And then because we're going to use the ideal gas equation, right? So we're going to convert it into liter, which is 0.933 liter. And then we know that the pressure that it's happening is at 99.3 kilonewton per meter square. Okay, and we know that 1 ATM consists of 101325 Newton per meter square. So we need to cross multiplication in order to find the value of x here. So lastly, we're going to get by using a comparison, we're going to get the value of X going to be 0.98 atm. So we have our pressure, we have our volume, and then we have our mass, and we need to use the ideal gas equation in order to determine the relative molecular mass of gas Y. Okay, so the temperature here is also given, which is at 31 degrees Celsius, in which you need to convert it into Kelvin. So we need to find the number of mole first in order to find the molecular mass. So we're going to use PV is equal to nRT, and then the pressure here is 0.98 atm by our conversion here. And then our volume is obtained by the volume of water, which is 0.933 liter. And then we need to find the number of mole, which is N. The R here is the gas constant, which is 0.08206 liter atm per mole per Kelvin. And then our temperature here is 31 degrees Celsius, right? And then you need to convert it into Kelvin by adding with 273.15. So we're going to get 304.15. So Kelvin and per Kelvin can be cancelled out. And then liter and liter going to be cancelled out. ATM and ATM going to be cancelled out. And what we're going to left is the unit of mole here. So it's referred to the number of mole. So once we do the maths, we're going to get the number of mole of the gas Y here referred to 0.03663 mole. Okay, and from here you can find the molecular mass by multiplying by dividing mass with the mole in order to get the molar mass. So for the molar mass, we're going to divide the mass with the mole. So the mass that you obtain, which is 2.54, will be divided by the mole that you just obtained from the ideal gas equation. So mass divided by the mole, you're going to get it to be 69.33 gram per mole. Okay, but remember, the question asks you about the relative molecular mass. So you have to compare the molar mass with 1/12 of the carbon-12. So relative atomic mass of gas Y gonna be 69.33 AMU divided by 1/12 of the carbon-12. So AMU and AMU, which is it refers to the atomic mass unit, gonna be cancelled out, and here refer to 1. So we're gonna get 69.33 only without any unit. Okay, so this is how we answer tutorial question 5. For question 6, a gas mixture containing 2.45 gram of nitrogen and 3.10 gram of neon occupies a volume of 2.5 liter. What is the total pressure of the gases at 25 degrees Celsius? So you can imagine that if you having two gases in the flask. So you have nitrogen gas and then you have a neon gas. So the nitrogen gas will have a mass of 2.45 and then the neon gonna have a mass of 3.10 gram. And then the total volume of the container gonna be 2.5 liter. So we need to find the total pressure. So in order to find the total pressure, we need to identify the total number of mole first. Okay, and we can obtain the total pressure by doing PV is equal to nRT, in which our total pressure PT is equal to NT here. So once we figure out the NT, we can use the ideal gas equation in order to figure out the PT. So let us find the number of mole of the nitrogen gas first. So for the number of mole of the nitrogen, it's going to be mass divided by molar mass. So the mass here going to be 2.45 gram divided by the molar mass of the nitrogen, which is 2 times multiplied by 14. And once you do the maths here, you're going to get 0.0875 mole. And then you need to find the moles of the neon, which is the similar step, mass divided by molar mass. So the mass of the neon is 3.10 divided by the molar mass of the neon, which is 20. And then once you do the maths here, you're gonna get 0.155 mole. So when we obtain the individual number of mole, we can add it up together to find the total number of mole, which is the number of mole of nitrogen add up with the total number of neon. So once we do that, we're gonna get the total number of mole to be 0.2425 mole. So from here, you have know the total number of the mole. And then for R is the gas constant, and then the temperature is 25 degrees Celsius, which is 2.9298.15 Kelvin. And the volume here is given, so you can find the PT. So PTV is equal to NT over RT, and then your volume is known to be 2.5 liter, and then your total number of mole is given as 0.2425 mole, and then R is your gas constant, and then temperature is 298.15 Kelvin, in which the degree Celsius you have to convert it to Kelvin by adding 273.15. So from here, mole and per mole can be cancelled out, per Kelvin and Kelvin can be cancelled out, liter with liter can be cancelled out, so you only have the unit of ATM. So once you do the maths here and divide by 2.5, you're gonna get the total pressure to be 2.37 ATM. So this is how you do tutorial question 6. For tutorial question 7, by using the water displacement method, 128 ml of oxygen gas was collected from the decomposition of the potassium chlorate, KClO3, at 24 degrees Celsius and at an atmospheric pressure of 762 millimeter mercury. So we have to calculate the mass of the oxygen gas obtained. The vapor pressure of water at 24 degrees Celsius was given to be 24 millimeter mercury. So here the keyword here is they are using the water displacement method. So in your mind, you need to be able to visualize this diagram here. So when there is a decomposition of the potassium chlorate, so the oxygen gas will be passes through the tubing here, and it will passes through the water, and it is collected up to the flask here. So in this region here, they're gonna have a pressure from the oxygen, which is given out from the decomposition, as well as the partial pressure of the water itself, because water can evaporate at any temperature and at any condition. So at this part here, the total pressure here is contributed by the oxygen as well as the water vapor from the surrounding. So you know that the total pressure is equal to P partial pressure of oxygen with partial pressure of water vapor, and then you need to find the partial pressure of the oxygen, in which the total pressure here is given as 762 millimeter mercury, deduct with the partial pressure of the water. So lastly, you're going to get the partial pressure of oxygen going to be 738 millimeter mercury. And the 738 millimeter mercury, you can convert that with ATM to ATM, because you know that 760 millimeter mercury is equal to 1 ATM. So let's say if you have 738 millimeter mercury, then it is referring to X ATM. So you can do a cross multiplication, and then once you do that, you're gonna get the ATM gonna be 0.971 ATM. So from here, you can calculate the number of mole first, because you know that the pressure PO2 PV equal to nRT. So we have P oxygen, so the number of mole here gonna be number of mole of oxygen. So the volume is already known, which is 128 ml, but we have to convert that into liter. Okay, so it's going to be 0.128 liter divided by 1000. So kena guna dalam unit liter. And then the number of mole is something that we need to find out. The R is the gas constant, and then the temperature here is 24 degrees Celsius, which you can convert that into Kelvin. So we're going to find the number of mole of oxygen first. So PV is equal to nRT. So our pressure here is given as 0.971. And then our volume need to be in the unit of liter. So we need to find out the number of mole. R is 0.08206 liter atm per mole per Kelvin. And then the temperature is 297.15 Kelvin. So per Kelvin and Kelvin can be cancelled out. ATM and ATM can be cancelled out. And then liter and liter can be cancelled out. So you're going to have the unit of mole. Okay, so once you do the maths here, you're going to get the number of mole of the oxygen, which is here PO2, and then nitrogen is NO2 here. So the number of mole of oxygen is going to be 5.097 times 10 to the power of negative 3 mole. Okay, and this is why you have to convert it into ATM so that it can cancel out. Similarly, that is why you convert milliliter to liter so that it can be cancelled out on both sides. So from the number of mole of oxygen, you can find the mass by multiplying it with the molar mass of oxygen, which is 32. So 5.097 times 10 to the power of negative 3 mole multiplied by 32 gram per mole. And finally, you're going to get the mass of oxygen going to be 0.163 gram. Okay, so this is how you answer the question related to the water displacement method. So for tutorial question 8, we need to describe the differences between the ideal gas equation as well as the van der Waals equation. So when we are talking about the differences, I think we should start with the equation itself. So for the ideal gas equation, we have the equation to be PV is equal to nRT. Meanwhile, for the real gas equation or the van der Waals equation, so they have the similar meaning. So it's going to be P plus N square A divided by V square multiplied by V minus NB is equal to nRT here. So in this real gas equation, we're going to include the attractive forces of N square A over V square, and we're going to minus the molecular volume of NB here. So you know that in the ideal gas equation, we're going to ignore the molecular volume of the gas because we have stated that the volume of the gas is very, very small and it is not significant. And as a result, we're just gonna assume that it is negligible. However, in the real gas equation, the molecular volume is significant. And as a result, the gas volume for the real gas is corrected using NB term here, in order to take into account the volume of the gas molecule. And this is needed so that we can get the effective volume of the container. Because effective volume is equal to V of the container, volume of the container, minus the volume of the molecule. In this situation here, which is in the ideal gas, we're just going to assume that the effective volume is equal to the volume of the container. Okay, and that is why the NB term is included in the real gas equation. Next differences is we have the term N square A over V square, which is in the real gas equation, and this is something to do with the attractive forces. So in the ideal gas equation, we're going to say that the gas particle going to be far apart from one another, in which they don't going to have any attractive or repulsive force between one another. And as a result, the intermolecular forces going to be negligible and ignored. However, for the real gas equation, there going to be attractive forces between one molecule to another. For example, like a dipole-dipole forces or the London dispersion forces and so on. So in the real gas equation, they take into account the attractive forces from one molecule to another. And as a result, the factor of N square over V square is used to correct the real gas pressure in order to include the attractive forces. And that is why we need to add up with N square over V square here. Alright, so I think that's all for today's video. See you again some other time. Bye!